Hi there, and welcome to my presentation. My name is Noroozi, and I'm from University of Munich. And in this presentation, I'm going to tell you how to develop a scale-free small-gain conditions, which are not only sufficient, but also necessary for input-to-state stability of a network system. Well, this is a joint work with Andrei Miroshchenko and Fabian Wirth from University of Passau. First of all, let's see why we need scale-free tools for analysis and design of a network system. Well, to provide sustainable solutions for our society, we are going to use emerging technologies to create a new generation of infrastructures where we are connecting all such infrastructures to each other and optimize them as a whole. Well, by doing so, we would provide much more flexibility and autonomy for the system. However, this comes with a price, and the price would be a large amount of complexity and uncertainty which would be injected to the system. And in particular, if we look at the whole picture, we will see that what a literally huge network we will have. And in fact, this is exactly where the problem arises. And the problem is our standard tools for analysis and design of control systems do not scale to the size of such emerging networks. In fact, as already well identified by the experts from different application areas, if the size of the system becomes larger and larger, then at a certain point, the system loses its functionality. It becomes unstable. And this is exactly what we must avoid. Well, having discussed why scalability matters, now let's see how to address this problem, and in particular, how to make stability and performance indices independent from the size of the system. Well, here's the methodology that we're going to take in this presentation to address, well, the scalability issue. Well, given a network system like this, the first step to address this scalability issue is to over-approximate the original network by an so-called infinite network, which contains infinitely many subsystems. And in fact, this infinite network can be considered as the limit case of the original network in terms of the number of participating agents. All right, well, focusing on this over-approximated network, we will show that this network satisfies some certain desired stability properties. But now remember that this is not our original network, meaning that at the next step, we need to truncate this network and get back to the original one. But here, the most important thing is that we need to make sure that all such nice properties that we have already obtained for the over-approximated network will be preserved under this truncation for the original network. All right, this is how this approach works. But now in terms of the technical tool to make this happen, in this paper, in this presentation in particular, we're going to use a small gain theory, which is a quite powerful tool for analysis and design of network systems. And in fact, the small gain theorems for infinite networks have been already developed, and here you can refer to two of the most recent contributions in this context. But the problem with all such contributions in the context of infinite networks is that all these contributions are inherently conservative in a certain sense that I'm going to explain to you in a second at the next slide. Well, to see why and where this conservatism comes from, let me briefly go over classic small gain theory, and then you see, it turns out why this approach is in general conservative. Well, given a network system like this, the first step is to decompose the whole network into the individuals. And here in this presentation, I would assume that each of these individuals is represented by a difference equation. And in particular, this guy collects the internal inputs, roughly speaking, the influence from the neighboring subsystems. All right, now we would assume that we want to establish input to stability for the overall network. Okay, this is our goal in terms of the desired property that we want to establish for the system. And well, this concept, as most of you know, is originally developed by Zontag. And here in this paper, and I'm sorry, in this presentation, I would focus on exponential input to stability, just to keep everything as simple as possible and convey the main message to you. And this property is also pictorially illustrated here. But if you look into our paper, you see a more general setting. Okay. All right. Now, having this desired property as our goal, then at the next step, at the second step, we enforce each subsystem to individually satisfy this property. Okay, so this means that if so at the second step, each of these individuals also needs to satisfy the same property as the one we have for the overall network. And finally, at the third step, we need to make sure that all these coupling gains, the interaction between systems, is small enough, which is quantitatively can be described by small gain conditions. All right, now if all these conditions are met, then we are in business, in the sense that we can conclude input to stability of the overall network from those of the individuals. However, if you look into these steps, you see that the second step sounds quite conservative, because input to stability is the property that we wanted to only have it for the overall network. I mean, this is only needed for the overall system. However, we are enforcing this property on every single subsystem, which is too much. And in fact, this is due to viewing, well, neighboring systems as disturbances. However, in general, subsystems may have a stabilizing effect on each other. And this is exactly our contribution. We want to exploit this potential stabilizing effect. And now let's see how to bring this into action and how to integrate this stabilizing effect with the underlying idea behind the small gain theory, so that at the end of the day we can come up with non-conservative small gain theorems, which are not only sufficient but also necessary. All right. Well, we'll see this stabilizing effect. What we're going to do is to look into the future behavior of the system. And to see this and to bring this into action, we use the concept of finite-step Lyapunov functions, and we integrate this concept with the underlying idea behind the small gain theory. Now let's see what we mean by a finite-step Lyapunov function. Well, given the overall network, which is denoted by sigma and whose details can be seen here, a function v is called a finite-step Lyapunov function if it satisfies these two properties. And in particular, the second item gives the distinguishing feature of this type of Lyapunov function in comparison with classical Lyapunov function, because we have this positive integer m, which can be larger than 1. And in fact, if I let the inputs 0, then we see that this this kind of Lyapunov function only needs to decay every m time steps rather than every single time step. And obviously, this is some sort of relaxation. And in fact, this is the relaxation that I'm gonna exploit to introduce non-conservative small gain theorems. I mean, to address the conservatism behind the classic small gain theory. All right, now let's see how to integrate a finite-step Lyapunov functions with the underlying idea behind a small gain theory. All right, so here are our main assumptions. And the first condition here will ask to have such a, some kind of finite-step Lyapunov-like condition for each subsystem. And the second condition asks for some uniformity on the gain functions, which are coming from the forward condition here. And finally, we have a small gain condition, which asks all the coupling gains between the subsystems to be less than or equal this alpha, which lies between 0 and 1. Well, it might seem that this condition will kind of conservative, but I'm going to show you in a second that it's not the case. And in fact, as long as we are interested in exponential input stability, this condition is necessary. Okay, so here's our first contribution. It says, if all these three types of conditions are met, then we are in business, meaning that the overall network is exponentially input stable. And also the other way around, meaning that if the network is exponentially input stable, then there exists Wi's, M, and all such coupling, all such gain functions, so that these three conditions are satisfied. Okay, so by the way, if you're wondering how we can construct the overall finite-step Lyapunov function from those of individuals, this is how we construct our Lyapunov function, finite-step Lyapunov function. And finally, this constructed Lyapunov function satisfies these two properties. Okay, now let's see what if we truncate our network, our infinite network, and see if such coupling, such stability indices will be preserved under the truncation or not. So, and here's our result. It says if M is 1, then we are in business, in a sense that the input stability indices C, rho, and gamma will be preserved under any truncation of the infinite network. Well, it might be not quite surprising that we have this M equal 1 and to have such results if M is 1. But well, very recently, we have extended our result to the case where M is larger than 1, which will be published very soon. All right, now finally, let's see how effective would be our result if we apply to some application. And in particular, here towards the end of the talk, I would focus on this application where we consider a traffic network which is divided into infinitely many cells as illustrated here. And each cell is described by this differential equation. And now if the overall network satisfies our small gain conditions, then it turns out that no matter how many participating agents we have, the general behavior of the network remains almost identically. And this is exactly what we wanted to show. I mean, because this indicates that the stability or performance indices of the system are independent from the size of the network. And this will indicate the effectiveness of our result. All right, with this, I would come to the end of my talk, and thank you all for your attention. If you have any questions, feel free to contact me by my email. Keep it safe and stay healthy. Thank you.